All right, so how was the test? Why are we showing that? Oh, that's moving. I have to quit this window first. How many of me do you see? There we go. All right, kind people. I think we're back on track. All right, so first by screen 20. Okay. All right, so last time oh, there's update Keynote. Last time we started looking at the elementary probability. And elementary probability was simply trying to figure out the probability of an event. The key thing about that event is uncertain. Yes? When you flip a coin or when you're about to flip a coin, you cannot tell what will happen. Okay? You get on the road right here, you're driving down to Miami, you cannot tell what will happen. Right? The AC might go out. There might be traffic on the road, so you get there late. There might be great driving conditions, and so you get there really early, right? You can't really tell what's going to happen, right? And so what we have to do is we have to have some way of kind of figuring out and conveying the probability or the chance that an uncertain event will happen. Make sense? And so we come up with these things called probabilities. And what a probability does right here is that it tells you the likelihood of an event happening. A probability lies between 0 and 1. Yes? A probability of 0 means the event will never occur. A probability of 1 means the event is guaranteed to occur. Yes? An example, if you're rolling a die, one die, what's the probability you get a 12 on a single roll? The answer is 0. That will never occur. Yes? Yes? Probability you flip a coin and you get either a heads or a tails, that's certain to occur. That's 100% chance of occurring when you flip that coin. Yes? I guess I should say flip the coin, heads or tails, or it lands on its side. Exactly. That's falling there to be more precise. Yes? No? No? And so that's what probabilities do. They don't tell us what will happen, they give us the chance, and so we can get a feeling of how likely it will happen. Right? And so if I tell you, hey, I have a 90% chance of scoring on this next shot I'm doing right here, right? You're more likely to recognize and understand that will happen, yes? And so you can make plans. So for example, if you want to make a bet, that's more of a bet that you're likely to make because you know there's a high probability or high chance that it will happen. Does it guarantee that I will score a goal on this next chance? No, it does not. It does not, right? But it just tells you the likelihood of it happening. The way that likelihood is described is something called a long run event, right? If I do that same event over and over and over again, say 10,000 times, say 100,000 times, say 1,000,000 times, if the probability of it happening is 90%, it means 90% of those 100,000 events will have that occurring. Yes? And so it gives you a feel for what will happen in the long run. Question there. And that actually allows us or gives us control over probabilities. A car insurance company cannot tell you, hey, this person is going to have a car accident. They cannot tell you, hey, person B is going to have a car accident tomorrow. They can't do that, yes? But somehow they can figure out a way to insure everybody, yes? And what they do is they look at the long run. If you have 10,000 people driving their car, I can tell you the probability is 1%, right? Maybe or 0.1%. Maybe 10 of them will have an accident out of those 10,000 people. And that allows me to then make plans. Yes? Questions? There are three kinds of probabilities. There is the empirical probability. That's when we just do the event over and over and over and over again. And that tends to be used when we have a complex scenario that we can't really understand. Yes? Like, for example, baseball games. Baseball games are very, very, very difficult to predict, right? What we can do is just look at the last state, and we can kind of have a feel of what's going to happen next. Yes? And then you have theoretical probabilities. And those, we often use them when you have more simplified scenarios. We can analyze each step of the process and then kind of figure out what will happen next. Yes? For example, flipping a coin, or deciding the probability that the next child for parents either be a boy or a girl. And the last one right here is that's just making an assumption about the probability. It's our intuition, right? Intuition is a cross between our experience and our hopes and our dreams, right? And so intuition has nothing to do with reality. No, nothing to do with reality at all. Yes. And so that often is where people get in trouble when it comes, for example, to gambling, because they often rely on their intuition. This team is my team, or this team has won the last 5 games, or this team has this star player. And so, you have the intuition is that they're going to win. Yes? And often that can be very diverse, very far away from actual reality. And that's how the people steal your money. And so that's why I always tell my students, if you're gambling, you should be gambling for fun. So you should go there, get $20, and when your $20 are gone, I had fun giving you my $20. Yes, yes, yes. If you want to be, there are professional gamblers. And if you look at those people, they take their job seriously. Got the World Series of poker and all those things right here. The people who actually win these things, they spend hours and hours and hours studying. They don't just show up and say, I'm going to win today, and then just start betting. Every single bet they do a calculation to figure out how much money they need to put down. It's not random, right? Right? Same thing with sports betting. Same thing the people in it's not Arizona, where most of the betting houses are in Vegas. These people are notorious for the hard work that they do, right? And so you have to keep that in mind if you want to go up against these people. A key part of theoretical probability is something called the sample space. Anybody remembers what the sample space is? Don't you all raise your hand at the same time? A collection or a list of all possible events. That's often our first step in developing a theoretical probability, is to try and figure out what could happen, right? And then once I figure that out, I can then go ahead and assign a probability. This is less likely to happen. I'll give you a 10%. This is more likely to happen. I'll give you a 50%. Or 50, 80%. But for example, flipping a coin, the sample space is either going to be heads or tails, yes? And when we analyze that, we can say, well, there's a 50% chance of getting heads and a 50% chance of getting tails, because there are two possibilities and the coin is fair. Yes. You guys know that coins don't have to be fair, right? Right? And of course, there's the famous heads I win, tails you lose. You never said that for your super coin? I do it all the time. No? Heads I win, tails you lose? No. If it's heads, if it's tails, exactly. Heads I win, tails. No, really? Really? All right. All right, so that's where we stopped. And so we'll take that into, you had a little bit more longer soliloquy since, it's been so long since I've seen you guys. It's been a while. All right, so we're finishing off 4.1, elementary probability. That's what our good friend Watson said. So you got a little bit of reminder right here. Again, your sample space is your list or a collection of all your possible outcomes. If I ask you to select a day of the week, what will be that sample space? Days of the week. So it'll be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Yes? That will be your sample space. All right. And again, if I wanted to analyze this process, if each day had an equal chance of being selected, then the probability of a Monday would be 1 out of 7. Yes? But if, for example, this is work and I know I don't work on Sundays and I don't work on Saturdays, then the probability of me working on Monday will be 1 out of 5. Yes? Again, analyzing the situation. Yes? If, for example, I know I only teach on Monday, Wednesday, Friday, then the probability of me teaching on Monday is 1 out of 3. The probability of me teaching on Sunday is 0, right? Because I don't teach on Sundays. Yes? Yes? And so that's why it's important to get the sample space. Determining the child's gender for a family of 2 children, assuming that the probability of having a girl is equal, as likely as equal to having a boy. Use B for boy and G for girl. What's going to be the sample space for this one right here? So the key thing right here is how big is the family? The family will have 2 children, right? And so each sample space has to have 2 items. One for the first child and one for the second child. And so the sample space is going to be this. Either both children are boys, or the first is a boy and the second is a girl, or the first is a girl and the second is a boy, or both of them are girls. And that will be our sample space. Because I'm only having 2 children, these are the only 4 possibilities. Questions there? Interestingly enough, there's an interesting pattern right here. If they had 3 children, there have been 8 probabilities. It would double because there are 2 choices, boy or girl each time. If they had 4 children, there would be 16 possibilities. I think one of your homework questions asked you to list out all 16 of them. Yeah, the first one is going to be all boys, and the last one is going to be all girls, or vice versa. And then the rest just goes crazy. I tell you. And so that takes us to one of the most important tools that we will have in our tool belt when it comes to analyzing sample spaces, and something that we like to call affectionately the FCP. No? I said FCP. That's what just make you feel happy and make you, no? The FCP, the fundamental counting principle. Exactly. Let's just make it, oh, you know what? I'm ready. Just give me the test now. I'm so interested. The FCP, the fundamental counting principle. The fundamental counting principle gives you the total number of outcomes. You see in the previous example, there were 4 possibilities, yes? I actually figured out before we did this right here, there are going to be 4 possibilities before I wrote them down. Right, there are 2 ways to do it. You can write down all the possibilities and count them, yes. Or you can figure out how many possibilities there are going to be 4. Yes? That's actually how I know that if there were 3 children, there are going to be 8 possibilities that I got to list out. Right? And if there are 4 children, it's going to be 16. I use this thing right here called the fundamental counting principle. It gives us the number of possible outcomes for a sequence. The key thing, or the key way that the fundamental counting principle works right here is that it does something called multiplication. You ever heard of this thing called multiplication? Yes, multiplication. You ever heard of that? Right. The fundamental counting principle says that when you're looking at the question that you're trying to work on, you have to determine how many steps are in this problem right here. In this problem right here, how many steps are there? 2. My first step is to choose the first child's gender. And then my second step is to choose the second child's gender. Yes? So your fundamental counting principle says you got to break this down right here into steps. I'll put it up here. into steps or decisions. So steps right here. So in this case right here, step 1 is the first child. And then step 2 will be the second child. And then all you have to do is simply select how many options there are. For the first child, how many options do we have? 2 options, yes? And so then I'm going to put a 2 right here. For the second child, how many options do we have? Either a boy or a girl, right? The fundamental counting principle says you simply multiply each of these together, and that will give you the total number, the number of outcomes. All right? Remember I said, what happens if they, instead of having 2 children, they have 3 children? That means I would have a third step, yes? I forget this thing doesn't have a delete button. Then you put it on here. So again, a third child. How many options do I have for my third child? 2 options. So I multiply 2 times 2 times 2. That gives me the answer of, there are going to be 8 possibilities for listing out how many children, what types of children or the mix of children that a family can have. Questions there? Questions there? Do you want to see me list out all 8 of them? All right, cool. Uh-oh. So this right here, no children exist. The first choice is either the first child is going to be a boy or the first child is going to be a girl. That's my 2 options, right? This right here is my first child. Then from there, now they've had the first child, the second child will come. That second child will either be a boy or a girl. Yes? Similarly, if the first child was a girl, then my possibilities will either be a boy or a girl. Is that okay? This is what I'm doing right here. I'm doing what's called a decision tree. So this right here is the second child. And then one more child to go. So if the family had 2 boys, then the last option will either be another boy or another girl. If they had a boy followed by a girl, then the options would be a boy or a girl. If they had a girl followed by a boy, then the options would be either a boy or a girl. And then the last girl, if they had 2 girls, then the options would be either a boy or a girl. Questions there? Questions there? That's going to be the choice for the third child. So I asked, do you want me to write out the list? So let's go. The first one right here is boy, boy, and boy. That's my first option right here. Then my next option is a boy, boy, and a girl. See what I'm doing right here? So my first option is I have 3 boys. My second option is the first 2 are a boy, and then the next one is a girl. And then I keep going. Boy, girl, boy. And then boy, girl, girl. And then notice this is halfway, right? Notice this is halfway, right? How many do I have so far? I got 4 of them, yes? And so how am I going to end up with at the end? I'm going to end up the 8 I'm looking for. Then girl, boy, boy. Then girl, boy, girl. Then girl, girl, boy. And then the last one, girl, girl, girl. Girl, girl. They have 8 options right here. 1, 2, 3, 4, 5, 6, 7, 8. Those are your 8 possible families you can have if you have 3 children. If you have 3 children, those are the only possibilities that you can have. Questions there? Questions there? The way that the fundamental counting principle works right here is then the first one right here is 2, yes? But because I have 2 options in each, I'm going to double that. So that's why they're multiplying by 2. And now I have 2 more options on each. And so again, I multiply by 2 again. And so it ends up being 2 times 2 times 2. That's why you're multiplying. That's why the fundamental counting principle is a multiplication process. Questions there? Comments? Queries? So if, for example, I wanted to list out a family of 4 children, I would just need to do one more branch in my tree. Yeah. Obviously, I'm going to run out of space. But a family of 4, I need just do one more branch in each of them, and that'll give me my 16 outcome. Question two. Yeah, no one's going to ask you to do a family of 5. Oh, my bad. You want me to ask you guys to do a family of 5? Oh. Whew. Yes. No, this is normal. This is normal. This is how everybody teaches you are. A long time ago, when I was doing math, my professor told us that, right, math has to be interesting, right? If we just come here and you just draw on, right? But the reality is math is interesting, and you have to find a way to convey that to the people. So I'll be trying desperately. Can't you tell? See, I'm sweating desperately. Can't you tell? Do, 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 do. That's how it's supposed to work. Anyways, questions. All right, so this person right here has a fair coin. They're going to toss it 3 times, and then they're going to roll a die with 6 sides right here. And the question is, what is the sample space? Can you write out all of the possible outcomes? Yes? And so for a question like this, often what we want to do first is just figure out how big is the sample space going to be, and that can kind of help us figure out what to do next. Yes? So how many times are we going to toss the coin? Uh-oh. Let me think I clear all that out. So put it back. Play. So how many times am I going to toss this coin right here? 3 times. So the first toss, the second, the third toss. And each time right here, I am tossing it. How many possibilities are there? Either heads or tails, yes? And then when I roll the die, how many possibilities are there? 6. And so to find out the total number of possibilities, or to count the total number of possibilities, I simply need to multiply all of these together. 2 times 2 is 4, 4 times 2 is 8, 8 times 6 is 48, and so there'll be 48 possibilities. Toss 1, toss 2, the die, 2 times 2 times 2 times 6, and so that'll give us 48 possibilities. And that makes it a little bit easier for us to write them out, right? For example, the first one is, the first one is going to be, I might get heads, and I get 1 on when I roll the die. That's one of the 48 possibilities. Hmm? Oh, I missed one. Oh, you're right. And we heads 3 times, and then number 1 right here. That's one possible outcome. Yes? Because I know there are 48 of them, this actually has a 1 in 48 chance of happening. This has a 1 in 48 chance of happening. Because there are 48 outcomes, this is one of those 48 outcomes, assuming everything is fair. Fair coin and a fair die. I did tell you guys I have a fake die, unfair die of my office, right? All right, cool. So we should gamble together. Yeah. I would not deliberately take your money. No. Well, actually, you're supposed to. Always. All right. So let's say you are getting ready for school, right? You're getting ready for school, and you gotta get yourself a backpack, a pencil, and some shoes, and say head on down to the bookstore. When you get to the bookstore, you see 3 backpacks that might work for you, 4 pencils that might work for you, 2 computers that might work for you, and 3 shoes that might work for you. Yes? How many different combinations? How many different possible ways can you select a set of tools that you need for school? Go ahead and see if you can figure that number for me, please. I know the answer is not 10 million. Another way to ask this question right here is how many different ways can you select a backpack, a pencil, computer, and shoes without repetition? That's a different way of asking the same question. I'm going to get one backpack, one pencil, one computer, and one shoe. And how many different ways can I make a selection without repetition? Right? At some point, I can go back and then get the same backpack, the same pencil, the same computer, and the same shoe, right? And keep going. But in how many unique ways can we make the selection? And the answer is 72. And the answer is there are 72 different possibilities. Questions there? If you wanted to write out the possibilities, you do the same tree that I did a while ago. So in that same, I'm not going to actually do it right here. In that same tree right here, you would have a backpack 1, backpack 2, and backpack 3, because there are 3 possibilities for backpacks, maybe a blue one, a green one, and then a red one. And then you have 4 pencils, so you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? And so forth and so on. And they keep branching out, getting bigger and bigger and bigger. Yes? What is 3 times 4? There are 12 branches so far, right? Because there started 3 and I got 4 each. 3 times 4 is 12. That's why the fundamental principle of counting is a multiplication process. Questions there? All right, cool. We already did this one right here. Another a pizza example. If you had 3 types of crust to choose from, you're supposed to use an example that relates to the common man, and apparently all students eat pizza. Yeah. Okay, back in the day, all students used to eat pizza. I don't know. And so you had 3 crusts, 3 cheeses, and 10 toppings. And so you just multiply them together, and that gives you that you can eat for 90 straight days and get a different pizza for every single day. But on the 91st day, you must repeat. Okay? If you want to go through all the pizza types, at the 90th day, you'd have done them all. You'd have to then start again. Questions there? Again, a different way of saying the same thing. All right, so you're gonna pause right. Oh, this is another example right here. Family has 3 children. I read this example right here, a boy or girl right here. There are 8 possibilities, and these right here are your 8 possibilities. Yes? Question. What is the probability that all 3 children are girls? Now we've done the first part of counting and breaking out the sample space. We can now move into the probability. Look at this setup right here. Each setup is equally likely to occur. What is the probability that a family will have 3 girls? It'll be 1 out of a total of 8. Yes? The number of outcomes is 1 because there's actually exactly 1 with 3 girls out of a total of 8. Let me rephrase the question. What's the probability of having 2 girls? What's the probability of out of the 3 having 2 girls? What's that probability? 3 out of 8. Remember, probability has to be between 0 out of 1, yeah? Between 0 and 1, yeah? So let's count. This one has 2 girls. This one has 2 girls. This one has 2 girls. And so the answer is 3 out of 8. Questions there? Let me ask you the hard question then. What is the probability of having at least 1 girl? What is the probability of having at least 1 girl? Let everybody make up their mind. Let everybody make up their mind. All right, first of all, do you understand the question? At least 1 means 1 or more, correct? 1 is fine, 2 is fine, 3 is fine, yes? And so this one has at least 1. This one has at least 1. Oh, look at that. This one has at least 1. And a total of 7. Answer is going to be 7 out of 8. So you guys were correct. Give yourself a pat on the back. Back in the day, you could get back there. But I'm getting old, people. Shut my face. Questions? Questions? All right. What's the probability of having one boy and one girl? What's the probability of having one boy and one girl? What's the probability of having one boy and one girl? What's that going to be? You think or you know? What's the probability of having one boy and one girl? Yes, what's the probability of having one boy and one girl? If it's impossible, then the probability is? It's going to be 0. That's right. You cannot have, out of 3 children, you cannot have one boy and one girl. That's not possible. Yes? Questions there? Cool. What's the probability all 3 children are the same gender? It is 2 out of 8. That is either you have all boys or all girls, and so that's going to be 2 out of 8, which is simplifies to 1/4. On your handy dandy calculator is 0.25. Questions there? Now, the thing about these right here, there are millions of ways to ask these questions. And so, you just have to, I would say much about the English, you have to read the English carefully, make sure you understand what they're saying. All right? What's the probability of having at least 2 girls? What's that probability going to be? 4 out of 8? At least 2 means 2 or 3, right? 2 or more, yes? And so 1, 2, 3, 4. You guys are correct. It's going to be 4 out of 8. I am paused. Any questions? Comments? Queries? Concerns? Yes.
It's really not that big. I was just thinking because my mom has 4 girls, but generally, but I don't know. I was just thinking.
Yeah, because the men's has one of each, it's still 50-50%. That's why it's still 50% that you have of each. In society, if you look in society, you generally have more women than men. But there are 2 main reasons for that. Is one, women tend to live longer, and with wars and stuff like that, men tend to be the people who go off, get shipped off to wars. Those are the main 2 reasons that we don't have gender balance in society. They tend to be more women than men, but only by a small amount. All right. But yeah, but to have if you have 4 children, all 4 of them are girls, the probability of that happening right here and G. Remember, there are 16 possibilities, is 1 out of 16 chance of that happening, which is what's 1 divided by 16? 1 divided by 16 is 0.0, is about a 6% chance of that happening. Yes, very unlikely. Questions? Yeah, it's like me. I come from St. Lucia. There are 150, 160,000 people in the country out of the world of 8 billion. And so very unlikely to meet one of us. Yes, very low probability there. All right, the complement of a set. The complement of a set is the probability that an event does not occur. If, for example, the chance of rain today is 90%, what's the probability that there will not rain today? Or if there will not be any rain today, what's that probability going to be? It's going to be 10%, yes? In this example, they say the chance of rain is 60%, then there is a 40% chance that it will not rain. This not rain, this is called the complement of the set. Yes? The complement of A is the probability that A does not occur. We use this symbology right here, a C or a slash, to represent the complement of a set. When you take the probability and its complement and add them together, the answer is always 100%. The answer is always 1. Right? 60% plus 40% gives me 100% chance. 100%. Yes? Questions there? I have a set right here. The set A is numbers that are greater than 4. So that's 5 and 6. Again, we're doing the die. The complement of that set right here are numbers that are not greater than 4. That's going to be the numbers 1, 2, 3, and 4. Questions there? Again, we use either a C and or a slash to represent the complement of the set. I believe for Weber sign, they use AC mainly for your complement of your set. Again, I could write this out here. The probability of this event happening is going to be 2 out of 6. The probability of that event happening is going to be 4 out of 6. Yes? If you add them together, you get one whole. 4 out of 6 plus 2 out of 6 gives us 6 out of 6. Questions there? So it means if I give you one, you automatically know the other. Right? So because that they only ever give you one, right? They always only give you one because you know what the other one's going to be. Questions there? All right, cool. Can I step forward? All right. What's the writing? All right, cool. So the rule of complements is that if you add the probability of an event plus the probability of its complement, the answer is going to be 1 or 100% if you're changing it into percentages. Remember, you can express probabilities as either a decimal or a percentage. All right. So either way is fine. The probability that an event does not occur, simply subtract from 1. Sorry. Excuse me. It's simply subtract from 1. So the probability that it's going to rain today is 40%. So the probability that it does not rain today is going to be 1 minus 40%, which is going to be 60%. Yes? Yes? Or should I guess I should write 100%, huh? 1, 0, 0. Question there about the rule of complements. All right. That takes us to the more important one, the at least one probability. We did this a little bit early on. When we say at least one, what does that mean in English? One or more, correct? Right? Right? So in terms of the children, that's either one girl or 2 girls or 3 girls. Yes? One or more. Yes? Anybody happens to know what the complement of at least one is? You haven't till I finish writing. You haven't said it yet. Complement of at least one is, drumroll, there we go. Complement of at least one is none. The opposite of saying I want at least one girl is saying I want none of them. Right? One or more. 1 is fine, 2 is fine, 3 is fine. What am I leaving out? 0, correct? And this right here is something that you must remember because it saves you a lot of time, as they're about to demonstrate right here. But the complement of at least one is none. So the probability of at least one girl is the same thing as the probability as 1 minus the probability that none of them are girls. Okay, I'm using the rule of complements right here. Yes? Remember, we already did this, right? The answer is 7 out of 8. Yes? Remember what I did? I counted all of them. There were 7 of them where they had at least one girl. Yes? This is a different way to get to the same answer. The probability that none of them are girls is the probability all of them are boys. Anybody remembers what's the probability of getting 3 boys? 1 out of 8. And so 1 out of 8. So 1 minus 1 out of 8 is 7 out of 8. We get to the same answer. Question done. The nice thing right here about this process right here, using the none right here, is that often we actually cannot find this directly, right? If I ask, what's the probability that at least one of you will have a green shoe? That probability is really hard. You got what, 25 people in here, and then I gotta try and figure, right? But if I go back and ask what's the probability that none of you have a green chair, have a green shoe, I can use that to figure out this probability. Yes? I go 1 minus the probability that none of you have a green shoe, and then that gives me my answer immediately. Questions there? All right. I have a fair-sided die, and it's going to be rolled how many times? Oh my goodness, 7 times. Who wants to do a sample space for that? The first toss, 6 chances. The second toss, 6 chances. The third toss, 6. And so it's going to be 6 times, 6 times, 6 times, 6 times, 6 times, 6 times 6 to get the total sample space. Yes? Yeah. Yes, 6 to the 7th power. Yes, 6 to the 7th power. Right? What is the probability it comes up 4 at least once? Now let me do this for you so you can see right here. 6 raised to the 7th power. Oh, that's not a raised button. 6 raised to the 7th power is 2,700 and 279,936 different possibilities. Yes? Who wants to go through all of these possibilities and count how many times you get a 4? Who wants to do that? Exactly, right? It turns out you can instead it's much easier to figure out the probability of having no 4s at all, and then going 1 minus that number instead. So let's roll. All right, so the complement of having at least 4 is having none of them give you a 4. Yeah. So what's the probability of not getting a 4? The probability of getting a 4 is 1 minus the probability it comes up a 4. Does that make sense? So the probability of not getting a 4 is going to be 5 out of 6. Getting a 4 is 1 out of 6. So not getting a 4 is 5 out of 6. Does that make sense to you? Does that make sense to you? All right. And so then the question is, how many times am I tossing this coin? 7 times. And each time I'm not going to get a 4, right? Because I want the probability of having no 4s at all. Yeah. And so that is going to be, on my first roll, I don't get a 4. On my second roll, I don't get a 4. On my third roll, I don't get a 4, and so forth and so on. And so that's going to be 5 out of 6 times 5 out of 6 times 5, 7 times. Right? First roll, I didn't get a 4. Second roll, I didn't get a 4. Third roll, I didn't get a 4. So that's 5 out of 6 each time. Yes? You multiply those together. In other words, 5 out of 6 to the 7th power. And then I subtract that from 1. Does it make sense why I'm subtracting out of 1? This by itself, 5 out of 6 raised to the 7th power, is the probability that I do not get any 4s. My first roll, I didn't get a 4, 5 out of 6. My second roll, I didn't get a 4, 5 out of 6, 7 times. Yes? Subtract that from 1, and that gives me my answer. The answer is there is a 72% chance, 72.1% chance that you will not get a 4. No, sorry, you get at least 1 4 if you roll the dice 7 times. Questions there? And so people who play in the World Series of Poker or whatever, well, they're asking themselves, what's the probability I get at least how many cards they have in the hand? I know 2 cards and like 5 cards coming down. If the 2 already are aces, what's the probability I get 1 more ace? They actually do the calculation. Yes, because 3 aces is going to give you a high probability of winning, right? They sit down and they do those. Actually, they have most of them memorized, but they do those calculations and they can say, okay, you know what? I have a 2% chance of this happening. If someone over here has one ace, that goes down to a 0.4% chance of winning, right? And so you start thinking right here, three people dropped out, me versus this one guy right here. These people are thinking. They're not just saying, I feel like he had no ace. That is not what's happening here. Questions there? And so let's answer it right here. Again, this should make sense to you right here. I'm rolling the dice 7 times. At least one time I get a 4 out of the 7 times. That's kind of a high probability. It's not like I'm just rolling it once and trying to get a 4, right? Right? And so the high probability of me getting a 4 right here. Questions there? All right. I think we're good. All right. Our last thing, I can send us on our way. Yeah, I can stop right here. A die has 12 sides. Have you ever seen a 12-sided die before? All right. Find the probability of rolling a number less than 5. What's that probability going to be? 4 out of 12. Yes or no? Maybe so. The key thing right here is out of the 12 of them, they said less than 5, so there are 4 numbers. And so then it is indeed 4 out of 12 or 1/3. Questions there? If they said right here, if they said rolling a number less than or equal to 5 or equal, then a 5 will get put in here, yes? Yeah. And then this would become 5 out of 12. Yes, if I make a small change to the English, I'm still using the number 5, yes? If I make a small change to the English, the probability will change. Yes? Okay. What's the probability of rolling a number greater than 5? Greater than 5. That's 6, 7, 8, 9, 10, 11. Did you get 7? There we go. So it's going to be 7 out of 12. Questions? All right, again, what's the probability of getting a 7 and an 8 on a single row? No. 0. I can't roll it and get 2 numbers at the same time. Yes? Yes, and so that's it's not possible. And so therefore the probability is going to be 0. I am out of time. Let's roll again, 1, 2, or 3. 3 out of 12. That's right. 1/4. I'm paused right here. I'm about to stop. Any questions? All right, cool. All right, let me take attendance. And then I can send you guys